about the properties of electromagnetic wave propagation in an anisotropic media. So first of all, we have to familiarize, or we have to know what is the basic difference between isotropic medium and anisotropic medium. Okay, let's. I'm going to share the presentation. BPT is visible. Okay. Now, in practice, there are some materials. Those are basically the anisotropic materials in which the optical properties depend on the direction of propagation as well as the polarization of the light waves. In place of light waves, we can also say that the polarization of electromagnetic wave. So those are basically the optically anisotropic materials. So the first point is clear. There are some materials whose optical properties mainly depend on the direction of direction of propagation, as well as the polarization of the electromagnetic waves. These are basically known as optically anisotropic materials. For example, you can say what should be the example of anisotropic materials? Different types of crystals like calcite, quartz, KDP. KDP means that is the potassium dihydrogen phosphate, and the liquid crystals. So these are the three examples of anisotropic materials: calcite, quartz, KDP, and liquid crystals. So this type of anisotropic materials, or this kind of crystals, they exhibit different types of peculiar optical phenomena. Throughout the syllabus, we learn different types of this kind of peculiar optical phenomena like double refraction, optical rotation, polarization effects, and the electro-optical and acousto-optical effects. So these kind of optically anisotropic materials, they exhibit different types of peculiar phenomena like double refraction, optical rotations, polarization effects, etc. So one by one, we will learn, or we will discuss more details about about this type of phenomena like double refraction, optical rotation, etc. Now, by using this type of peculiar phenomena of the anisotropic materials, different types of optical devices are made. Different types of optical devices are like, you can say, that is the prism polarizer, sheet polarizer. Prism polarizer, sheet polarizer, and birepresent filters. So these are different types of optical devices that are made with the help of optically anisotropic materials, and this type of devices can be made only with the help of anisotropic materials due to their peculiar phenomena or properties. So to understand the wave propagation in an anisotropic media, we have to thoroughly understand the light propagation or electromagnetic propagation in an anisotropic media. Because with the help of this type of anisotropic media, we can make different types of optical devices which are very useful in practice. So mainly from this discussion, or from this first slide, we can conclude that the anisotropic media means, or anisotropic materials means, their optical properties will depend, or depends on the direction of propagation as well as the polarization of the electromagnetic waves or light waves. Now, as I have mentioned, first we have to know the what is isotropic material. If you can remember the properties of isotropic media from the basic knowledge of electromagnetic theory, you know that in case of isotropic media, the polarization is always proportional to the electric field, as well as it is parallel to the electric field, that is in the direction of applied electric field. Okay, in case of isotropic material, or isotropic material means that is basically the linear medium. In case of linear medium, polarization is always proportional to the applied electric field. At the same time, it will be parallel to the applied electric field. That means the induced polarization will be in the direction of applied electric field. But in case of anisotropic media, this particular point is not valid, that the direction of propagation may not be in the same direction of the applied electric field. That is, in case of anisotropic materials, the induced polarization may not be in the same direction of the driving electric field or applied electric field. Okay, that is the main difference between the basic of isotropic medium and anisotropic medium. In case of anisotropic materials, the induced polarization may not be in the same direction to the applied or driving electric field. So the question is, why the induced polarization is not in the direction of driving electric field in case of anisotropic media? To get the answer of this particular point or particular question, we have to go in details about the structure of the anisotropic media. Then it will be clear why the induced polarization is not in the direction of driving electric field. So what is the source? If I ask you that what is the source of polarization in a material? In a material, that may be isotropic, that may be anisotropic. Point is that in any kind of material, what is the source of polarization or induced polarization? That is the electric charges. Okay, that is the electric charges. Electric charges in a material are the source of polarization. Now these electric charges, they are bounded or connected to the neighboring nuclei. So the blue color is representing the nuclei, and these are the electric charges. So the electric charges are connected to the neighboring nuclei like a mass on a spring. If you consider in that way, that the charges, electric charges, they are connected to the neighboring nuclei like a mass on a spring. So these are the spring through which the electric charges are connected to the neighboring nuclei. So if we consider this type of inner structure or molecular structure for a particular materials, that may be isotropic, that may be anisotropic, we are basically concentrating on the molecular structure of the anisotropic materials. So now in case of anisotropic material, the stiffness or the strength of this spring by which the electric charges are connected with the nuclei are not same. That is the most important point. In case of anisotropic material, the strength of these springs through which the electric charges are connected with the nuclei are not same. That means you can say the strength of this spring is not equal to the strength of this spring. So the electric charges are connected with the nuclei with the help of a spring, like a spring mass on a spring, but the strength of the springs are not same for all the electric charges. As a result, what will happen? But in case of, if you consider the case of isotropic material, the situation is same. The electric charges are connected with the neighboring nuclei like a mass on a string. But in that case, but in case of isotropic materials, the strength of these connecting strings are equal. Whereas in case of anisotropic material, the strength of these springs are not equal. Due to this unequalness of the strength of the spring, the electrostatic potential will not be symmetric in nature or structure. So we can say the electric charges are seated in a particular potential well, electrostatic potential well. The shape of this potential well are basically depends on the strength of the spring, as the strength of the spring are not same for each and every electric charges. So we can say that in case of anisotropic material, the electric charges are seated in an electrostatic potential well which is not symmetric, in nature. That means you can say if you consider a particular charge and if you consider the corresponding electric well, electrostatic potential well, next you consider another charge and you consider the another electrostatic potential well. These two potential wells or these neighboring potential wells will not be equal or symmetric in shape with respect to each other. Particularly for that reason, the induced polarization may not be in the same direction of the to the applied or driving electric field. As the charges are seated in an electrostatic potential well which is not symmetric in structure, so in case of anisotropic material, the induced polarization may not be in the same direction to the direction of in the direction of applied electric field. Is it clear? Anyone from your side, is it clear or is there any doubt? The electrostatic potential well in which the charges are seated, they are not symmetric in structure, means they are basically the ellipsoid in nature. So the charges are seated in a kind of ellipsoidal potential well, and due to this type of structure of the potential well, the induced polarization will not be or may not be in the direction of driving electric field. Now this point I have already mentioned that is the example of anisotropic materials or crystals. They are basically the different types of crystals like calcite, quartz, KDP and the liquid crystals. These are the best example of anisotropic materials. Now they exhibit different types of optical phenomena, peculiar optical phenomena. Why we are mentioning that peculiar optical phenomena? It will be clear when we will discuss in more detail about the corresponding phenomena. So the peculiar phenomena like double refraction, optical rotation, and the conical refraction. These are the different types of peculiar optical phenomena exhibited by the anisotropic materials. Now, as we have mentioned that in case of anisotropic material, the induced polarization may not be in the direction of applied electric field. So now we have to consider that. So that means the polarization, induced polarization, is related with the applied electric field, obviously. Now the induced polarization P is related with the applied electric field by this particular equation. P equal to epsilon 0 xi E, where you know the epsilon 0 is the dielectric constant of the materials, or you can say the permittivity of the material. What about the xi? Xi is the susceptibility of the material. Could you please tell me what do you mean by susceptibility? Susceptibility of the material? Hello, anyone? What do you mean by the susceptibility of the medium or material? The class is going on, or the link is, or there is any internet problem?
স্যার আছি, বাট মনে পড়ছে না।
Okay, then I have to explain, or I have to tell you what is the susceptibility. If we explain the susceptibility of the material in short, it is basically the tolerance of the materials. Tolerance of the materials to which parameter or point, which particular point, it is the tolerance of the materials to all sources of interfering electromagnetic energy. So it is basically the tolerance of the materials to all sources of interfering electromagnetic energy. That means the greater the electric susceptibility, the greater the ability of a material to polarize in response to the applied electric field. If the susceptibility of the material is higher, that means its ability of the corresponding material to polarize, that will be also higher, and thereby it will reduce the total electric field inside the material. Is the definition or explanation is clear regarding the susceptibility? It is basically the tolerance of the materials to all kind of source of electromagnetic interfering energy. Now, as it is the tolerance of the material to the interfering electromagnetic energy, so if the susceptibility of a particular material is higher, that means ability of the corresponding material to polarize will be also higher, and as a result, what will happen? The total electric field inside the material will also reduce. Now, with this simple definition and the explanation of the susceptibility, now susceptibility is basically represented by tensor of rank 2. Now, if I ask you that, what do you mean by tensor? The susceptibility of the material is basically represented by a tensor of rank 2. In other sense, you can say it can be represented by a matrix. Now, my question is, what do you mean by tensor? Tensor is scalar or vector? Still, there is no question, answer. Okay.
It
Basically,
is
a
neither a
scalar.
vector quantity, it is neither a vector or scalar quantity.
Yes, that means the tensor are the basically the, or in other sense we can say the scalar or vector are the special cases of tensor.
Tensor, yes, sir.
Okay, if tensor has only magnitude and no direction, that means what will be its rank? Rank will be 0. So the tensor with a rank 0, that are basically the scalar quantity. Clear? That means you can say the tensor is the generalized form version of vector or scalar quantity. if the tensor has rank 0, that means only magnitude, no direction, then the rank of the corresponding tensor is 0 and it will represent a scalar quantity. Now, if a tensor has magnitude and one direction, at least one direction means what will be the rank of the corresponding tensor? Rank will be 1. Then it will be called, or then it is called the vector. Clear? So if the tensor has rank 0, that means it has only magnitude, no direction, it will represent a scalar quantity. If the tensor has at least one direction along with the magnitude, then it will be called the tensor with rank 1 and it will represent a vector quantity. So the tensor is basically the generalized form of vectors and scalars. So this susceptibility of the material is represented by a rank 2 tensor. That means that is a vector quantity with two directions. Rank 2 means two directions, and as well as it can be represented in a matrix form. Now, as in previous slide, in this particular slide, we have seen that the induced polarization is related with the driving electric field by this equation, P equal to epsilon 0 xi E, where xi is the susceptibility and epsilon 0 is the dielectric constant. So now this dielectric constant, instead of using the dielectric constant, we can represent it in terms of tensor form, that is dielectric tensor. So next we are going to discuss about the dielectric tensor. This permittivity or the dielectric constant of the materials, as we know from the basic material property, the displacement vector is related with the electric field vector by this equation d equal to epsilon E. That is the case of isotropic material. Now, in case of anisotropic material, that equation becomes this following one: d equal to epsilon 0 E plus P. D equal to epsilon 0 E plus P. Now, in these equations, if we put P equal to epsilon 0 xi E, that is the polarization vector, where xi is the susceptibility tensor. So, from this equation, from this particular equation of P, we can write this polarization in 3 cross 3 matrix format: Px, Py, Pz, that is equal to epsilon 0, xi1 xi12, xi13, in that way. This is the susceptibility tensor. The coefficient xij, that is within this matrix, these are called basically the electric susceptibility tensor. So this is the electric susceptibility tensor, that is a 3 cross 3 matrix. Now, if we only consider if we vanish the off-diagonal elements, then from the previous matrix we can write down that Px equal to this one, Py equal to this one, and Pz equal to this one. So the material property, from the material property, d equal to epsilon E, that is epsilon 0 E plus P, that is for the anisotropic material. Now in this equation, if we consider P equal to, if you put P in terms of xi, that is epsilon 0 xi E, then epsilon becomes epsilon 0 1 plus xi. That particular dielectric constant, now that means in this equation we have represented the dielectric permittivity in terms of tensor, so it becomes the dielectric permittivity tensor. Again, from this equation it has been written as in this particular form: d equal to epsilon 0 1 plus xi E, where this particular one, epsilon 0 plus 1 plus xi, that is the dielectric permittivity tensor. Now, if we only consider the ith component of the displacement vector di, we can rewrite these equations in this particular form. And then it has been written in this particular form, that is epsilon ij ej. In this equation, this epsilon ij, it is representing the dielectric permittivity tensor, that is epsilon ij equal to epsilon 0 into 1 plus xij, is xi of ij. Now in case of lossless medium, these dielectric tensors are Hermitian in nature. Hermitian means, their complex conjugate will be equal, or epsilon, if the dielectric tensor is represented in terms of complex number, then it will be epsilon ij equal to epsilon ij star. If it is not represented by the complex number, then it will be only epsilon ij equal to epsilon of ji. That means for an anisotropic materials, this dielectric permittivity tensor, they are Hermitian in nature. They should be Hermitian in nature because if the corresponding material has to follow the conservation of electromagnetic field energy, in that case, this dielectric permittivity tensor must be Hermitian in nature. We'll in the next few slides, we have to prove that that how these dielectric permittivity tensors are Hermitian in nature and they are equal. So for the conservation of electromagnetic field energy, the dielectric permittivity tensor must be Hermitian in nature. That means epsilon ij equal to epsilon ji. If it is represented by the complex number, then it will be epsilon ij equal to epsilon ji star. That is, the complex conjugate will be equal. Now, before going to proof of the corresponding Hermitian nature of the dielectric tensor, if we consider that epsilon ij equal to epsilon ji, that means now if you consider the corresponding dielectric tensor, that will be 3 cross 3 matrix, epsilon 1 1 to epsilon 1 3, epsilon 1 2 to epsilon 2 3, epsilon 1 3 to epsilon 3 3. Now these parameters are equal. This epsilon 1 2 equal to epsilon 2 1. There was basically epsilon 2 1. It was basically epsilon 2 1. It was basically epsilon 3 1. It was basically epsilon 3 2. Now, as they are Hermitian in nature, so they are equal. This epsilon 1 2 and epsilon 2 1 are equal. Epsilon 1 3 and epsilon 3 1 are equal. Similarly, epsilon 2 3 and epsilon 3 2 are equal. So instead of 9 elements, there are all total 9 elements. So due to the Hermitian in nature, we can represent or we can describe the corresponding dielectric tensor, dielectric permittivity tensor by only 6 elements. Now, you have to prove that particular point, that the dielectric tensor are Hermitian in nature, that is epsilon ij equal to epsilon ji. Now, to prove this one, we are starting with this particular point. What is UE? UE is the stored electric field energy. In the first class, most probably, we have discussed about the pointing theorems. Pointing theorem means total energy flow will be equal to the stored electric energy, stored magnetic energy, and the ohmic loss. So now we are only considering the stored electric energy. Electric energy stored due to the electric field. So UE equal to half of E dot D. Now as we know, D equal to epsilon E. So we can write down this one in this particular form, half of EI epsilon ij EJ, because we are considering that DI equal to epsilon ij EJ. Now if we consider the first order derivative, UE dot equal to half of epsilon ij is common term, so it becomes EI dot EJ plus EI into EJ dot. So this is directly we are getting from the stored electric energy in a particular material. Now you have to start with from the derivation of pointing theorem. From the derivation of Poynting theorem, you can directly write down this one, that is divergence of E cross H equal to E dot of D dot and H dot B dot. That is, it becomes equation number 3. Now E dot D means you can write down EI equal to epsilon ij Ej dot, that is H dot plus H dot B. Now instead of writing this equation directly, you can consider these last equations. How we are getting this last equation? Simply the Maxwell's equations. Curl E equal to minus del B del T. Minus del B del T means that is the minus of B dot. Now curl E is equal to, as per the Maxwell's equation, J plus del T del T. Now as we are considering the lossless medium means sigma 0. Sigma 0 means J will be also 0. So this term becomes 0. It only D dot. Okay. So now in this particular equation, if we dotting on both sides E, that is E dot of curl is, it becomes E dot of derivative of D, that is D dot. Now you consider the Poynting's theorem. That is, or simply if you consider the divergence of E cross H, divergence of E cross H, divergence of E cross H is basically the representing the rate of energy flow. E cross H is the S, so divergence of E cross H will represent the energy flow. Now divergence of E cross H, you can write down from the basic vector notation, that is equal to E dot of curl H minus H dot of curl E. So basically it has been rewritten or rearranged in this particular format. In place of E dot dd, you can write down this one, E dot of curl H. E dot of curl H. This is basically the E dot, sorry, only just vector sign of it dot E dot of curl H. Okay. So in place of E dot curl H, we have put this particular value from the previous equation, E dot D. Now from this equation, I think H dot curly. Curly means B dot. Curly means B dot. So H dot curl E. In place of H dot curl E, you can write down that H dot of B dot. So it becomes just H minus of divergence of E cross H, minus of divergence of E cross H, that is equal to this one, E dot of D dot. এই টার্মটা রাইট সাইডে চলে আসছে, so it becomes H dot B dot. এখানে একটা অলরেডি মাইনাস সাইন আছে, so it becomes plus, so it will be H dot B dot. That particular equation has been written, this last equation has been written directly in the previous slide. Okay, you see this equation. So we are getting this equation basically from the derivation of Poynting's theorem. Simply divergence of E cross H, you write down it in form of E dot of curl H minus H dot of curl E. Then you, in place of E dot curl H and H dot curl H, you use this equation, you use this particular Maxwell from the Maxwell's equations directly, then you will get these equations. So from the Poynting theorem derivation, we are getting these equations. This is basically the representing the rate of energy flow from a particular volume of the material. Now this E dot D can be represented in the tensor form, that is EI epsilon ij Ej dot. Now it remains as it is with the previous equations. This is the equation number 3. That means if you compare the right hand side, what is E dot D? What is this E dot D? It is basically the stored electric energy into the medium or into the material. So that means this UE dot, this equation number 2, it will be exactly same with this the first term of the right hand side. This is the stored electric energy. Whatever is this first term, this is the stored electric energy. This is the stored magnetic energy. Now, if you compare this equation number 2 with equation number 3, that means the first term of the right hand side of equation 3 will be equal to the equation number 2 that is written in the next slide. That is half of epsilon ij ei dot ej plus ei eg dot, that is equal to epsilon ij ei ej dot. এখানে একটা ডট আছে, এটা দেখা যাচ্ছে কিনা জানি না, ej dot. So from this equation 4, this equation 4 will be true only when this particular condition is valid. It is epsilon ij equal to epsilon ji. So in that way, we can say that if the equation 4 is to be true, then this epsilon ij will be equal to epsilon ji. And if the lossless medium is described with the help of complex dielectric tensor, then epsilon ij will be equal to epsilon ji of star. So their complex conjugate will be equal. So from in that way, we can prove that the dielectric tensor are Hermitian in nature, basically to satisfy the conservation of electromagnetic energy. Why we are saying that conservation of electromagnetic energy? From the point of conservation of electromagnetic energy, we can write down this particular equation only. From equation, by comparing equation number 2 with 3, we have only considered the stored electric energy, not the stored magnetic energy. So this stored electric energy of equation number 2, that must be equal with the stored electric energy of equation number 3 that has been written in equation number 4. And if this equation number 4 is true, then we can immediately write down that epsilon ij equal to epsilon ji. So you'll go through the corresponding slides. I think you'll be able to understand the proof of this particular point, that is the dielectric tensor of the materials are Hermitian in nature. Next, with this discussion, next we are moving to derive the wave equations for the propagation of electromagnetic field in an anisotropic materials. We are familiar with the wave equation in an isotropic materials from the basic of electromagnetic theory of BTech. Now we have to derive the wave equation for the propagation of electromagnetic wave in an anisotropic materials. So you see that we have started with the one is electric field, another is magnetic field. Electric field E equal to e to the power I omega t minus k dot r. K is the wave vector. We can write down this wave vector by these equations, you know, omega by c of s cap, where s is the unit vector along the direction of propagation, whatever would the n is the refractive index. Similarly, we can write down the corresponding magnetic field by this equation, h equal to by h of e to the power I omega t minus k dot r. Here r is the position vector. R is the position vector of the corresponding electric and magnetic field. K is the wave vector. K equal to omega by c n of s cap, where s is the unit vector along the direction of propagation. So once again, to rewrite the wave equation, we have to start with the Maxwell's equations, and we have to, as we are considering the dielectric, that means it is a lossless medium. Lossless medium. So rho equal to 0. What will be the J? J equal to sigma E. Actually, it is sigma. So it becomes 0. So the first equations from the Maxwell's, curl E equal to minus del B del T, we know. So we have written that equation in rearranging it. That is curl E plus del B del T equal to 0. Similarly, from the curl H, curl H equal to J of plus del D del T. It has been rearranged in this particular form, curl H minus del D del T equal to J. Now, so we can divide into two sections, one for electric field, another for the magnetic field. Now, in this equation, we can directly write down that J equal to 0. In place of J, we can write down J equal to 0. Now, we are using this one, del T equal to I of omega, and this grad operator, del operator by I of ik vector, I of k vector. Then these two equations can be rewrite in the following form, that is I of k cross E plus I omega B. Once again, this is for the electric field part, this is for the magnetic field part. I of k cross E plus I of omega B equal to 0. It becomes I of k cross H minus I of omega D equal to 0. Now, we are using the material relations, that is B equal to mu H, D equal to epsilon E, and J equal to 0 in the previous equations. So this K cross E, K cross E equal to, it becomes B equal to mu H, so it becomes minus of mu omega H. And from this equation, it becomes K cross H equal to omega epsilon E, because D equal to epsilon E and J equal to 0, so K cross H of omega epsilon E. Now, if we apply cross K cross on both sides of these equations, we are applying K cross on both sides of this equation, then we can rewrite this equation in this particular form, K cross of K cross E minus of mu omega K cross H. Now, from the previous equation, you can put the value of K cross H equal to omega epsilon E. So this equation becomes K cross of K cross E minus, that is equal to minus of mu, that is omega epsilon E. So it becomes mu omega square epsilon E. If you rearrange it, it becomes, this is the equation, K cross of K cross E minus omega square mu epsilon E. This is the wave equation in an anisotropic materials, where this dielectric constant, this is, it is basically considered as the diagonal in the principal coordinate system, that is epsilon equal to epsilon x, epsilon y, epsilon z only. All the off diagonal matrix is 0, elements are 0. Now in this equation, K cross E, if you want to write down this particular wave equation in matrix form, then it is better to rewrite these equations, that is K cross of K cross E, by this one. That is, if you write down this K cross of K cross E, you can write down that K of K dot E, আমি আর ভেক্টর সাইনগুলো ইউজ করছি না, K of K dot E minus K square E. Minus K square E. Next termটা যেমন আছে তেমনই থাকলো, that is omega square mu epsilon E omega square mu epsilon E that is equal to 0. So you can say this is the another form of wave equation in case of anisotropic materials. Okay. Now considering these last equations of the last form of the wave equation in an anisotropic materials, if you consider all the elements, then you can write down in this particular matrix form omega square mu epsilon x. I am not going to prove this one. You can check it. Omega square mu epsilon x minus ky square kz square kx ky kx kz. Then there will be the electric field vector ex ey z, that is equal to 0. Now for the non-trivial solution, obviously the determinant of this matrix must be 0. So for the non-trivial solutions, the determinant of this matrix must be 0. So we have considered the determinant of this matrix, that should be equal to 0. That is, we are representing it, say, equation number 1. Equation number 1. Now, this particular determinant, if you simplify this equation, it will basically represent a 3D surface in K space. To represent a 3D surface, three-dimensional surface in K space. Okay, and that particular surface is known as the normal surface. This is very important to analyze the property of an anisotropic materials. That's why from the wave equation we have considered its matrix form, and for the non-trivial solution the determinant should be 0. Now from this determinant of this particular equations, that is the equation number 1, it is basically representing a 3D surface in the K space, and this particular surface is known as normal surface. Now this normal surface, that means it basically consists of at least 2 shells. 2 shells that are that may be ellipsoidal, that may be sphere, but in case of anisotropic material, as we have mentioned, that the potential well are not symmetric in nature, rather than they are asymmetric. They are basically represented by the ellipsoidal structure. So this particular surface, 3D surface in K space, it will represent the overlapping of 2 shells which are not symmetric in structure. The 2 shells, the overlapping of the 2 shells are considering to represent this particular surface, that is known as the normal surface. So if you consider the overlapping of 2 shells, or better to move to the next slide. Oh, it is represented, it is directly mentioned. It is represented a 3D surface in K space, where K is the propagation vector, and the corresponding surface is known as normal surface. So it basically the consisting of 2 shells. So if you consider the overlapping of 2 shells, what will be the number of common points or crossover points? So instead of considering this structure, this complex structure, actually we have considered 2 shells in this particular figure, centered at the origin of this particular coordinate system, where the axes are representing kx, ky and kz. This is the origin of the 2 shells, or you can say the 2 potential wells, where the potential wells are not symmetric in structure, rather they are ellipsoid in nature. So, but their center is same. Center point is same. We are considering with the coincentric two shells. So if you consider two coincentric shells, better I am representing in that way. Say this is one ellipsoidal quantum well. So this is the common center point say, and I am considering another ellipsoidal quantum well, and the overlapping of these two shells, we are considering. So you can say for these two shells, the k value will be different. Say for it k1, for the this k2. So now that means it has for if you consider this type of overlapping between two shells that are not symmetric in structure, rather they are ellipsoid. So there will be at least 4 common point. 4 common point means this is one, this is another point, this is another point, and this is another point. So there are 4 common points. Now if you draw, so we can draw at least 2 lines. The condition is that the corresponding line must be passes through the origin of this or center of these two shells. So we can at least draw 2 lines. One is like that. So these are called optical axis. This is say optical axis 1. You can draw another lines. The crossover points, 2 crossover point, and the center of the two shells. So this is another optical axis. Wave 2. So this type of surface we can imagine or we can consider from the wave equations. We have considered the matrix form, then we have considered the determinant. For the non-trivial solution, determinant should be 0. From the determinant or from the last equations, it can be represented in a 3D surface, that is over the momentum space or k space. So it is basically the consideration of overlapping of two shells. They are concentric. So if you consider the overlapping of the two non-symmetric shells, so there will be at least 4 crossover points or the common points. So in that particular figure, this is the crossover point of the two shell. As we are considering from one side, in the another side there is another crossover point. So if you draw a line that is passing through the 2 crossover points and the center of the shell, that will represent the optical axis. Now, to analyze or basically to understand the property of the anisotropic materials, this normal surface is very important. At the same time, it is very important to identify the optical axis, because if the wave is propagating through the optical axis, it will face the only one phase velocity. But if it passes through any other axis rather than the optical axis, the corresponding wave will face 2 different phase velocities. How? Say, as I mentioned, one shell, the wave vector is represented by k1, k1. The another shell, it is represented by k2. We know k equal to omega by c n cap. Okay. Now, what about the phase velocity? Phase velocity is indirectly proportional to k. The phase velocity Vp equal to, we know phase velocity Vp equal to omega by k, omega by k. Now suppose this particular shell has k value of k1 and this particular shell has k value of k2. Now at this crossover point, what about the k? What about the value of k1 and k2? They are equal. So along the optical axis, the wave will face a single k value. A single k value means from this equation what will be its phase velocity? It will realize the single phase velocity. But if you consider any other than optical axis, that is, if you consider the wave propagation in any other direction apart from the optical axis, what about the situation? See, the wave propagating along this line, it is passing through the two shells at two different k value. At this point, k is k1. At this point, k is k2. So what about the phase velocity at this position? That will be omega by k1. At this point, it will be omega by k2. For this particular point, the anisotropic materials exhibit different types of peculiar optical phenomena. Okay, that will be discussed one by one in the next few classes. For the timing, is it clear about the normal surfaces? Because the discussion of the next few classes will depend on this particular point. Anyone from your side? Is there any doubt? From the simplified wave equations, we have represented in terms of a 3D surface. The 3D surface is basically we are drawing on the k space. That's why you have considered three axes kx, ky, and kz. Now, as we have mentioned that in case of anisotropic materials, the charges are seated in an potential well, where the potential wells are not symmetric as the stiffness of the spring are not same. So the corresponding potential wells are not symmetric in structure. Now, if you consider the overlapping of two such potential well, they will basically form the normal surface. Apart from the mathematical representation, just physically, if you think about the overlapping of two electric potential well, where the electric potential wells are not symmetric in structure, rather than they are basically the ellipsoid in nature. So if you consider the overlapping of two ellipsoid, there will be at least 4 crossover points. Now, if you can draw at least 2 lines that will passes through the two crossover points and the center of the two shells. Then it will represent the optical axis. Now, wave passing through the optical axis, it will phase only one k value, so it will realize only one phase velocity. It will not exhibit any kind of peculiar phenomena. But other than optical axis, that is, if wave passing through any other axis or along any other line apart from the optical axis, the corresponding wave will face two different k values. When it will cross one shell, it will face say k1. When it is passing through the another shell, it will face k2. So at two different points, it will face two different k values. So it will exhibit two different phase velocity. That is mentioned in this particular point. If the wave propagating in this particular direction, that means along the optical axis, it will face only one possible phase velocity. In any other direction other than the optical axis, it has two possible k values for two different shells. The same figure has been presented in this particular figure in more realistic form. Crossover of two shells. It has been drawn on the k space, kx, ky, kz. This is the common center point of the two shells. This is one crossover point. So we are considering there is another crossover point on the back side. So if you draw a line, it will represent the optical axis or optic axis. So wave propagating along this particular line, it will exhibit same speed, because the phase velocity will be only one phase velocity will be faced by this particular wave, as k value is 1. But if wave propagating in other directions, like in that case, will face two different k value at two different crossover point, phase velocity are different. Now the same set of equations, basically we have to identify the, it is mentioned that the phase velocity is represented by omega by k. Now from the previous equation, that is equation number 1, or from the wave equation, we can rewrite the, or to identify the direction of electric field, you can rewrite the equation in this particular form: Ex equal to E0 into this one, where E0 equal to Ex square plus Ey square into Ez square. So from this particular equation number 2, you can easily find out the direction of electric field. And next, as the wave propagation vector k equal to omega by c n of s cap. So the equation number, previous equation number 1 and 2, it can be rewrite in this particular form, that is in terms of the unit vector s, it is s is x whole square divided by n square minus epsilon x by epsilon 0. So equation number 1 can be rewrite in this particular form 4. Equation number 2 can be rewrite in this particular form, that is 4. Equation number 4. This particular equation number 3, it is known as the Fresnel's equations. It is basically, you can solve it to identify the refractive index, and from the equation number 4, it will give the direction of propagation. So these are the different form of corresponding wave equations. As per the requirement, you have to choose any one, either equation number 1 or 3, or you can choose equation number 2 or 4 as per the requirement. Now, if you, as we are discussing about the wave propagation in anisotropic media, so once again, if we consider the Gauss's law from the Maxwell's equation, that is divergence of D equal to rho. Now, in case of dielectric material, as we know that rho equal to 0. Now, this del operator is represented by ik cap, ik vector. So, I of k dot D equal to 0 from the Maxwell's equations. That means, what is the significance of this particular equation? That means the propagation vector, this is the propagation vector k, it is orthogonal to the k dot D equal to 0. That means k and D are orthogonal to each other. So from this equation, we have find out that the direction of propagation and the displacement vector are orthogonal to each other. The propagation vector k and the displacement vector d, they are orthogonal to each other. That means perpendicular to each other. But from the pointing vector, we know pointing vector is equal to e cross h. Is equal to e cross h means it basically gives the direction of energy flow. It gives the direction of energy flow. So this S is orthogonal. S is orthogonal to both, or you can say only the electric field. S equal to e cross h means this energy flow, it should be, if we consider E H, that will be the direction of energy flow. S E and that is H. So that is from Poynting theorem. Direction of energy flow, it will be orthogonal to the electric field. So from this equation, we have seen that propagation vector is orthogonal to the displacement vector. But from the pointing vector, we have seen that the direction of energy flow, that is S is orthogonal to E, but it is not orthogonal to the D. That means the energy will not flow in the direction of wave propagation until and unless the polarization wave is not an eigenvector of the material's dielectric tensor. Okay, that is the main point. So energy flow will not be in the direction of propagation of the electromagnetic wave until and unless the polarization of the wave is not eigenvector of the dielectric tensor, material dielectric tensor. So that is the basic discussion about the wave propagation in anisotropic materials. We have covered so far the discussion about the susceptibility tensor, dielectric tensor. We have proved that the dielectric tensor are Hermitian in nature. Then we have considered the wave equation for the propagation of electromagnetic wave in an anisotropic materials. From the wave propagation equations, we have formed the normal surface. In the normal surface, how we can define the optical axis and how the electromagnetic wave will face same speed or two different speed depending on the two different phase velocity that we have discussed so far. Now, depending on this discussion from the next class, in the next class, we will discuss about the index ellipsoid and different types of optical phenomena that are exhibited by the uh, anisotropic materials. So that's all. The rest of the part I will discuss in the next class, not today. Now, if you have any doubt, I don't know whether you are able to understand the discussion because it is only one-way communications. There is no interaction from your end. In last class, there was lot of interactions, lot of doubts, and I think I have sent the materials to clear your doubts that are helpful. I think now it's up to you. If you have no doubt or no queries, I have nothing to say. Only 14 out of 22.